Okay, so I'm gonna make a video for my exam 1 essay 2 questions. Um, the first question is explain how the resting membrane potential of the cell membrane is established. What properties, characteristics of the cell membrane account for the resting membrane potential's development? Okay, so I'm gonna go to a new page. For the resting membrane potential, resting membrane potential. Okay, so the resting membrane potential is the voltage difference across the inside of across the plasma membrane of a cell. And a lot of these happen at negative 70 millivolts. So say we have our graph. I'll label it real quick. A lot of it starts at negative 70 right there. When most of these are at negative 70 millivolts, which means the inside of the cell is predominantly negative. Let's see the next question. What conditions or factors affect the resting membrane potential's magnitude or size? So a lot of this has to do with ion gradients, ion concentration gradients, and a lot of this is sodium, potassium, and chloride. Chloride and proteins do quite a bit with this, but a lot of it is sodium and potassium. The ion gradients, potassium is usually super high on the inside of the cell, and sodium is pretty high on the outside of the cell. And they're selectively permeable. What conditions or factors affect the resting membrane's potential magnitude or size? Include a brief discussion of the Nernst equation and driving force. Okay. So since they're selectively permeable, there's more potassium leak channels, and if there's more potassium leak channels, it leaks. So potassium will flow out, which makes the inside of the cell more negative. There's also a sodium and potassium pump. So if you pump, say, 3 sodium ions out, then 2 potassium ions will go in. And this helps maintain the concentration gradient. If it's 300 on the inside and 250 on the outside, it helps just keep everything level. So a lot of these factors are the ion concentration gradients, membrane permeability, and the pump activity for those. For the Nernst equation, this is a driving force equation. Can write it out. I'm trying to memorize this equation. All right. So the Nernst equation is typically sorry, my iPad just went out for some reason. Here we go. All right, so we have N Nernst equation, and it has E equals negative 61.5 over Z, and Z is trying to think of the word. Z is the number that the ion is. So if it's chlorine, then it's -1. And then Z log of the inside of the cell over the outside of the cell. So just like that. And this will help us tell which way the ions will flow and things like that. Here's a good picture. Kind of like right here. You have a voltage gated channel. You see sodium coming in, and the activation gate, and the different charges on that picture. All right. Next question. In part 2 of this essay, discuss the action potential. List its characteristics, describe the events that take place during a typical action potential, including a description of the various phases: rising phase, falling phase, hyperpolarization, relative refractory period, absolute refractory period. For each phase, describe the actions and the channels involved in the ion's currents. Compare and contrast a graded potential with an action potential. Give an explanation of the capacitance and length constant. Describe how capacitance and length constant are affected by myelin. Okay, I'll definitely have to go back to that. But the characteristics of an action potential, all are they have different thresholds that must be reached for an action potential to occur. And in the question, it mentioned some of it was the rapid depolarization and repolarization. Trying to find my picture. Okay, so the propagation travels along the axon. And the refractory periods limit firing frequency and direction. So the resting phase is the negative 70 millivolts. And this is the voltage gated sodium and potassium channels. And when it's at the resting phase, it's closed. So this is the channel right here. This is a voltage gated sodium channel. And so with this one, for the channels to open, the sodium will rush into the cell, and the membrane will become more positive. So on the graph I had before, when that sodium rushes in, making it more positive, say it goes up to positive 30. So when it's at positive 30, that causes depolarization. And then we have what's the falling phase, where, say, this is open, but you're having a repolarization, the sodium channels become inactive. So the voltage gated potassium channels open, the potassium will flow out, and it'll bring that, I'll go back to it. It'll bring the millivolts back to its resting phase. And that's the falling phase, so repolarization and everything like that. Gotta go back to the question. Rising, falling phase, relative refractory period, absolute refractory period. For each phase, describe the actions of the channels involved, and ion currents. Compare and contrast a graded potential with an action potential. Give an explanation of capacitance and length constant. Describe how capacitance and length constants are affected by myelin. Okay, so we'll go over refractory period. That's where the sodium channels, go here. That's where these sodium channels remain open a little bit longer, and it allows the voltage to become a little more negative on that graph that I showed before. refractory period. Relative refractory period. Okay, so with that relative refractory period, it's where some sodium channels basically just get a little bit better, but the potassium channels are still open. And this can trigger an action potential. So when sodium rushes in, making it more positive, we have this springy thingy, what we like to call it, which will move up, which then causes this gate to open. So when the sodium rushes in, that's what's making this more positive. And the other way is where when the potassium channels, or when the potassium goes in, it brings it back to its resting state. Okay. Capacitance. Give an explanation of capacitance and length constant. Describe capacitance, length constant, cost. Myelin. Okay. So capacitance is the ability of the membrane to store charge. I don't think I have an example in here for that. But it's basically for capacitance is the ability of for a membrane to store charge, and the higher the capacitance, the slower the voltage change. And then the length constant is the distance over the amount of voltage that decays. So the distance of when voltage decays from its initial value along the axon. Yeah, I think that makes sense. But when it comes to capacitance and the length constant, myelin affects capacitance by decreasing it. When myelin decreases capacitance, then a faster membrane starts to charge. And then if it increases the length constant, then signals will travel farther with less decay. So I think it just helps it work a lot better. And then I think this, all in all, just makes it way faster and more efficient for signals to travel through your axon through your neurons, your axons to your dendrites, so that it can tell your body what's going on.